Good morning, everyone. So this is a video on the mechanical energy balance, Bernoulli's equations. So I wanted to go over that since yesterday or 2 days ago, I went over regular energy balances. This one is for mechanical energy balances, right? So the thing you want to remember with energy balances is that we typically find ourselves in one of two camps. Either we don't care about the mechanical side of things, and it's just a chemical energy balance, or we don't really care about the chemical side of things and we focus on the mechanical side of things, right? So as a refresher, let's just write out our full energy balance just like last time. Du dt is equal to Q plus shaft work plus the sum of inlet streams times specific enthalpies, subtract mass out times specific enthalpies minus change in kinetic energy minus change in potential energy. Now, you might recall from the previous video that the kinetic energy and potential energy terms were removed, which is pretty typical when we do chemical energy balances, right? There is no change really when we go through a reactor and the change in kinetic energy or potential energy. We're really just curious about, okay, what is the energy requirements that of the reactor, or how much energy is it releasing? So these things are more important than the kinetic energy or potential energy, so we just ignore them. However, there is a group of problems, and quite a lot of few problems that you'll see later on in transport, where there is actually no reaction, and what we do care about is the change in kinetic energy and potential energy. So, for example, we might have fluid just flowing through a pipe at two different heights. There's no reaction going on, it's just fluid going maybe from one unit operation to the other. But because there's a change in height and a change in the radius, so change in velocity, perhaps we have maybe we have an expander going on here. We do have changes in kinetic energy and potential energy, and we do care about what those changes are, because we do want to understand what's the energy going into the next unit operation. So in this kind of case, you have a lot of these terms start canceling out, and you're just left with the overall equation. So I'm not going to go into the derivation of the mechanical energy balance. I don't think it's worth your time. If you are curious, there's quite a few on the internet. You can search it up. I think Wikipedia also probably has a pretty good one. But essentially, what happens with this energy balance, assuming we're at steady state, we have an incompressible fluid, meaning our density is constant. We have friction forces are basically zero, so any friction loss due to viscosity is zero. We have no shaft work. So kind of like the example that you see in this pipe right here, right? What we end up getting is the mechanical energy balance known as the Bernoulli equation. And so using this, we can basically calculate, and for these assumptions, right? Steady state incompressible fluid, friction equals zero, and shaft work equals zero, the change in the energy state from one point to the other, right? Now, of course, as you get further on in your chemi journey, and you get to points where you're like in transport and friction terms don't go to zero, or you're not working with an incompressible fluid, then obviously the mathematics change a little bit, and you'll learn how to deal with it when you get to that point. But let's actually see um, this equation in practice, right? So suppose I have that same setup where I have, so we have a pipe like this, and I don't know, let's just say it expands a little bit at the end, just for funds. Change in height is 50 meters. Right here we have a half a centimeter inner diameter. At some pressure, we'll call it P1. And then it comes out, this is coming in, fluid comes out at a 1 centimeter inner diameter pipe, and this pressure is at atmospheric. So another thing you'll learn in transport 1 is typically when we are going outwards, as soon as it hits atmospheric pressure, that's the actual pressure of the fluid at the outlet. Okay, flow rate is 20 liters per minute. So our question then becomes, what is the pressure at the inlet? So when we're first looking at a problem like this, I think it helps to first check, hey, is the assumptions of the Bernoulli equation holding true, or is it reasonable to make those assumptions? I think it's reasonable to assume that we're at steady state. So that's checked off. This is water, 20 liters of water. So water is an incompressible fluid. So that's good. Friction equals 0. Yeah, that's fair. We can make that assumption. And lastly, shaft work, there's nothing. It's just fluid moving through a pipe. So, of course, shaft work equals 0. So we should be good to go in this case. So let's set up our overall balance. We have delta P over rho plus the delta in the velocity squared over 2 plus G delta Z equals 0. All right. So we need to find what are the terms in each part of the equation. Let's actually expand all these deltas here. So we have P2 minus P1 over rho plus U2 squared minus U1 squared over 2 plus G times Z2 minus Z1 equals 0. So let's actually figure out what each one of these values are and where we can substitute in. So we know that this Z2 and Z1, that's 50 meters, and we'll keep everything in meters since that's the unit. That's a very, very convenient unit for us. Okay, so that's 50 meters. We know that our pressure coming out the outlet, P2, is 1 atmosphere. Since we want to put this in SI units, we should convert this atmosphere into pascals, which is 1.01325 times 10 to the 5th pascals. And now we just need to find our velocities here, which we can easily do just by doing some simple unit conversions since we have a flow rate. So let's do U1. So we have 20 liters per minute. We know that there's 1 meter cubed for 1,000 liters. Then we can convert the area here. We know that the cross-sectional area will be pi times the inner radius squared. We also know that there is 10 to the 4th centimeters squared for every 1 meter squared, converting that to an area. And then lastly, of course, 1 minute to 60 seconds. And so we end up with getting U1 equals 17 meters per second. The only difference for that with U2 is that the cross-sectional area is pi times 0.5 squared, and we get a answer of 4.24 meters per second. Okay, so now we have all the values, so let's enter them into our equation. So we have 1.01325 times 10 to the 5th minus P1, which is our unknown, divided by the density. Density of water is 1 gram per centimeter cubed, or 1,000 kilograms per meter cubed, keeping everything in SI units, plus 4.24 squared minus 17 squared over 2, plus 50 times 9.8 meters per second squared equals 0. And now this is just algebra. We can solve for P1, which gives us 4.56 times 10 to the 5th pascals, which, converting into atmospheres, gives us roughly 4.5 atmospheres. This is the final answer. That's pretty much it. This is Bernoulli's energy balance. As you can see, it's just straight algebra. It's just a matter of putting things in proper units and making sure that you're putting them into the equation properly. All right, that's it for this video. And I'll see you guys in the next one.